I'm going to talk about some very basic but missing tools for doing something with the ancestral recombination graph. This is a problem I thought about for a number of years in puzzlement because I wanted to do things with the ancestral recombination graph and I was stymied by these fairly basic things. I need to figure out how to advance this. Right, so the ancestral recombination graph is a way of visualizing the history of regions of the genome that underwent recombination. So in this graph, the blue region has a topology where A and B are closely related. The red region of the gene has a topology where B and C are closely related. There's a recombination junction in the middle. And the ancestral recombination graph is defined by the fact that we assert that we know both where in the tree and where in the sequence the recombination occurred. They're reasonably easy to work with in terms of, for example, doing a likelihood analysis because every position in the tree sees a regular branching tree. They're distinct in that way from hybridization graphs where you don't know which part of the genome came from which ancestral species. Most genomes are really ARGs, and this fact is widely ignored because it's such a pain. If we don't deal with it correctly, one of the things that happens is that when you look across the genome and you see an area where there's much more genetic difference between individuals than usual, there's often a selectionist or a mutation rate interpretation of that that's very ready at hand. But that may also mean that in the ARG, that part of the genome is a little older by chance than the rest. The sequences are more different because they go back to more distant common ancestors, so we can misinterpret variation in mutation content. We can try to infer trees of things that are not trees, which there's a poster on that coming up, which I encourage you to look at, but it's well known to lead to trees that are, they're not just an average of the different recombinant trees. Recombinant lineages tend to move towards the base, like hybrids, it's a pain. We might chop our data into increasingly tiny bits, trying to find non-recombining parts. We might fail, but even if we succeed, this chopping up procedure is going to lose statistical power. And we might over-rely on parts of the genome that are known not to recombine, like mtDNA, the Y chromosome, and starve ourselves of the immense power of the nuclear genome. So why not just infer the ARG? There are actually existing programs, two existing programs that can probably do this. My own program, Lamarck, and the InfraRow program from Bruce Ranelag's group. But that's not what they're used for. They're used exclusively to infer population parameters like the recombination rate, gene conversion rate, effective population size, things like that. The fact that they are making multiple Bayesian-style inferences of the ARG behind the scenes is ignored. InfraRow won't even print out its ARGs, and Lamarck will do so only with a non-documented debugging flag. So it's obvious to ask, do they actually infer the ARG successfully? Have we written ARG inference engines and we don't even know it yet? That was actually a problem that bogged me for many years. Because in order to test if this works, you need to be able to say, is the ARG that comes out a good representation of, for example, the ARG in which you simulated your data? That needs an ARG distance metric. There wasn't one. It would also be super helpful. Both of these programs produce clouds of millions of ARGs. You can't look at that. It's difficult to do anything with it. For trees, one would use a consensus algorithm to make a consensus of all those ARGs and get some kind of story out of it that you could look at or publish or understand. Don't have a consensus algorithm for ARGs either. So this talk I'm going to try and very quickly develop both of those things. For ARG distances, we went with just about the most naive approach possible. We're going to start with a tree distance metric, such as Robinson folds or other distance metric of your choice. We're just going to compute it for each side along the sequence and average them together. How do we know if that's any good? There's an example of it here. I can't really point, but there's an ARG with 3 subtrees on top, P1, P2, P3, governing different parts of the sequence. There's an ARG on the bottom with Q1 and Q2. So for example, in the overlap of red and green, we're going to calculate the distance between P1 and Q1 with our tree metric of choice. In the overlap between blue and green, we're going to calculate the distance between P2 and Q1. We're just going to average them weighted by the number of sites that each one governs. How do you tell if that's any good? There's no gold standard for whether a distance is correct. Our idea was that as you increase the amount of data, ARG inference should get better if we have any ability to do it at all. And so a good distance metric is one that sees that trees made from ARGs made from more data are closer to the truth than ARGs made from less data. That seemed like a reasonable measure of whether the distance measure is any good. So we measured the percent of simulated data sets in which the high data solution was perceived as closer to the truth than the low data solution. And you get graphs for that. You can compare different distance measures. I won't go into the nitty details, except that very simple distance measures work well in this. It's better to look at branch lengths than not, because the trees that you're comparing are often very similar. And we showed in a comparison of distance metrics for non-ARGs, for regular trees, that when your trees are very similar, you really want to incorporate branch length information. Otherwise, you get way too many ties, trees with the same topology where you can't tell. So the Robinson-Folds method with lengths is a good choice. You can make it even better by just fidgeting the exponent a little bit. Robinson-Folds is really a family of methods with different exponents on the differences in clay content, and you can fidget the exponent downwards. It was embarrassing because I published a paper years ago in which we fidgeted it upwards on no evidence. It doesn't work. We also looked at this on non-recombining trees. Metrics with branch lengths are far, far superior for trees that are rather similar to each other. For example, if you're comparing different gene inferences of the same species tree, you really want to consider the branch lengths if your method gets them. Topology only is best if you're looking at very dissimilar trees, but that's a more limited zone of applicability. So there's a distance, and that's a good start. Now I'd really like to be able to get a consensus, because I find the cloud of a million ARGs a difficult thing to do anything fun with. The simple approach has a problem here. We could go with the same naivete. We could make a majority rule consensus tree at each site. Obviously, ones where there's no intervening recombination will be the same. So I could make a majority rule consensus tree for that region in which P1 and Q1 overlap. That would be the consensus of P1 and Q1 trees. And then I could switch to P2 and Q1 for that short segment there. The problem with this is that I'm forcing my consensus to have a breakpoint everywhere any of the ARGs that went into it has a breakpoint. If you put a million ARGs into that, you get a million breakpoints, millions of breakpoints. Your sequence is chopped into little bits. It's not at all satisfying that the consensus of a bunch of ARGs that have 2 or 3 recombinations each is an ARG with a million recombinations. That won't do it all. So there's also a hard approach where you take the tangled graph structure that I showed in an early slide and you try to make some kind of geometrical consensus of those tangled graph structures. Better minds than me have thought about that problem. For hybridization graphs, it is excruciatingly difficult. We made no progress with it. So I went back to the naive method and I tried to just improve it. And in particular, I'm trying to restrain the number of recombinations that go into my consensus so that it will be somewhat comparable to the number that are in the things it's consensing. There's a class of recombinations that really exist in data, really exist in simulation, and are really indetectable because the donor and recipient were each other's closest relatives in the tree, and you simply cannot tell even in principle. That's the tree on the most toward me with the little blib in it. You can't see those. If you're not looking at branch lengths, you also can't see the one in the middle. So for the moment, I'm going to ignore branch lengths. I'd like to do better in the future, but to get just a topological consensus, I'm going to ignore those guys. They are not going to contribute, so that reduces the number of recombinations going in. I'm also going to make use of the fact that these ARGs were presumably inferred from data. I've assumed sequence data, that the principle is the same. If I've got a run of sites that don't vary in my character matrix, I don't know where inside those the recombination breakpoint is. I may be completely sure that there's a recombination breakpoint somewhere in that run, but I don't know where it is. And the power of the data to tell me where it is extremely poor. So I'm going to collapse that into a single recombination location. So two trees that have a recombination in the same run of invariant sites, not in the same place, I'm going to treat them as the same. And that helped some. The third innovation is to say, I've got this huge cloud of ARGs. If I saw a recombination in a particular place in just one of them, I don't think I want to incorporate that into my consensus. It's not very well founded. So I'm going to use a threshold. I'm going to say that a breakpoint in a particular region only gets into the consensus if it reaches some threshold value. And that will again help restrain the infinite growth of the number of recombination breakpoints in my consensus tree. That's the key one, and I call the method threshold consensus because of it. Does this work? Well, we need a rule for what's a good consensus, which is actually missing in the literature. I decided on 2 rules. I'm aiming for something that has about the same number of breakpoints as the truth, that represents a recombinant history that's at least plausible given the recombinant histories that came out of our inference, and that it's closer to the truth than the average cloud member. Here you see why I needed a distance method, because I have to be able to define what closer is. I also asked about the closeness of the consensus to the cloud. and got the same results, which I won't show here. So when recombinations are scarce, you get a good count of breakpoints when the threshold is pretty low, about 5 to 10%, and your accuracy is good with any threshold. You get consensus that is closer to the truth than a random member of the cloud, which is gratifying. So the consensus is extracting information from the cloud about the true underlying arc that the data were simulated on. It's presenting to you, and it's better than picking a random member out of the cloud as a representation. And that was gratifying. If you dial up the recombination rate, you get relatively good breakpoint results with a low threshold. And here, threshold matters for accuracy as well. If you start being very conservative, if you start saying, I'm not going to consider a breakpoint unless it was in 50, 60, 80% of my arcs, you start to get to the point where your consensus is a worse representation of the truth than a random member of the cloud would be, which is undesirable. So the overall result of these simulations is that the threshold actually should be quite low. That surprised me very much. If a recombination shows up in even 5% of the trees in your cloud, it's worth considering putting it in. Something I didn't appreciate when I did this is that if you do that, you don't get as many recombinations as I thought. Because sometimes, even though you put a breakpoint in, it turns out that the trees on either side of it, the consensus trees are topologically identical. At that point, I take the breakpoint back out because it's a breakpoint separating two trees that are not different. So there's a certain amount of loss of excess breakpoints just from the consensus process, but it is still important to use the threshold. If you allow in everything, you do get too many recombinations in most cases. So the take-home message from this is that we can now compare ancestral recombination graphs in a simple but reasonable way, using a length-aware tree distance averaged across a sequence. There's a paper out on that. If you want to make a consensus of ancestral recombination graphs, you can use threshold consensus with a low threshold. 5 to 10% seems to work well. And that will get you something that is a reasonable depiction of what is known about the underlying true arc that you were trying to infer when you made this cloud in the first place, at least across the range of parameters to be explored. What this work is not is a real assessment yet of whether you can actually infer the arc with these programs. I will say that in simulated data where I pick the parameters to be quite permissive of arc inference, it performs very well. It makes less than one topological mistake on average amortized across the trees. Actually surprised me how good it was. Python code for both of these methods is available on Dryad. The links are in these papers. Where are we going to go with this? So I'd like to know when we can infer the arc. Is it realistic to hope that we can infer the arc of biological data, even in this limited sense where we're only focusing on the recombinations that change the tree topology? What program should we use? How long does it take? How big of a cloud do you need? Once that's done, I figure that biologists will find uses the same way that once people were able to draw phylogenies, people found enormous numbers of uses for knowing what the phylogeny of the organism was. To start with, we can avoid treating our non-tree-like data as if it were tree-like. We can look at the mapping of traits across the arc, which has potential for gene mapping that I think is only limitedly exploited. We can, in general, better understand what the history of recombining regions of the genome are and not be so afraid to venture out into the nuclear genome. The downside of all this, which I have to be honest about, is that both of the programs that I mentioned as being able to do this are not genomic scale programs. This is going to be the history of a modest sized region of the genome because the complexity of the arc grows by leaps and bounds as you get longer and longer sequences, and trying to do a chromosome is going to bite you. I'd like to thank Joe Felsenstein for helping hash out these algorithms, John Yamato for helping hash them out and coding most of them, and the National Science Foundation for being willing to fund this strange little piece of work. Thank you. Questions?
So when you make a consensus for bifurcating trees, the consensus is a multi-repeating tree. Do you have an idea that the consensus for an ARG should also be ARG?
I think that the consensus for an ARG should also be an ARG. I am not limiting my ARGs to having only one recombination at a given breakpoint, though, so it pretty well definitionally is. You could always make a set of recombinations. I'm not, with this method, recovering the recombination donor and recipient exactly. I cannot draw the tangle graph. What I know, and what I think all the data really bears on, is what's the branching tree governing each region and where are the region boundaries.
Oh,
The
okay.
attempt to recover the whole tangled graph is asking more from the data than is actually in the data, sadly.